Welcome in the arena. My name's Allyson Klein. Today, I am delighted to be having a episode about high performance computing and how technology is used to advance scientific discovery. It's one of my favorite topics. And to do so, I've got one of my good friends, Bill Magro, with me. Bill is the global director of high performance computing at Google, and Google is really transforming the way people think about HPC. Welcome to the program, Bill.
So thanks, Allison. I'm glad to be here, and thanks for the invitation.
Now, I know that Google really needs no introduction. I think everyone knows who Google is, but they may not be as familiar with Google's HPC business, and you've never been on the show before. Could you just walk us through how Google looks at HPC, what you're delivering to the market, and what is your role in all of that?
Well, as you said, Google's a household name. It's part of a larger company called Alphabet. And within Google, we have a number of different divisions, and Google Cloud is where I sit. Our approach to high-performance computing is maybe a little bit different than some others in the market. Google came to cloud and started its cloud offering a little bit later than some of the other players in the market. But one of the things that our customers really appreciate about us is a very thoughtful approach that Google has taken to the architecture and just the whole user experience. So I would say that, Google Cloud, something that's not necessarily very familiar to high-performance computing users, but maybe more broadly in the IT community, is something known as the Magic Quadrant, right? And Google's been moving steadily up and to the right, and up and to the right means capability and strategy, right? Your ability to execute, and then also your long-term strategy. So Google was making great progress, or Google Cloud rather, in establishing itself as a leader in the cloud industry. But in terms of high performance computing, really didn't have a dedicated product group, at least when I joined the company. So in terms of my role, it really was to come in and bring some of the high performance computing experience that I had, and look at Google Cloud's capabilities and offerings through the lens of an HPC user and someone who had spent the time in the industry building and delivering HPC systems to customers, and ensure that we had the right products. And product doesn't just mean things like virtual machines, storage, networking. It also means the tools, the engineering teams, the internal practices that really give you the confidence to say we can do high performance computing. We can, do things that are, comparable with what folks could do on premise, and then putting that narrative together so that we go talk to customers. So my role initially was to come in under a chief technologist title, but really look at things holistically and start to establish the right people, products, practices in order to approach high-performance computing users, and addressing the things that really they know and are important to them, to open the door for Google to bring in the things that it was already, I'll say, great at more broadly in cloud.
I think that a lot of people who are in the industry think about high performance computing as, kind of monolithic clusters that exist in national labs, the top 500. People also think of hyperscalers like Google as running massive data centers with incredible compute capability, but high performance workloads are unique. How do you tackle high performance workloads within a cloud environment, and how is that different?
Well, I think the key difference, and this is one of the things that kind of differentiates us maybe from some of the other folks out there, is that Google has really been innovative in the way it approaches building workloads. But because Google built its services up with a lot of, I'll call it, internal systems and a lot of inventions, there's a lot of innovation at Google. And Google's fairly open, right? Very, very big participant in the open source community. And so you can see what some of those innovations are, from networking to storage architectures to analytics and so on. And those, however, do require that you build the application in a way to take advantage of those innovations. And so kind of finding that impedance matching of how do people who are doing high performance computing in the traditional ways with compiled programming languages like Fortran, C, C++, CUDA, and running them with message passing systems such as MPI and Nickel. How does that compose with something that's truly a cloud native architecture? And so one of the biggest challenges, and it wasn't a huge technical challenge, it's just a matter of focus really, and bringing in, I'd say, folks with the right experience, was bringing those worlds together so that people can approach Google Cloud and not have to rewrite their workloads, not have to make really any changes. So our customers are able to bring their binaries in, their actual executables, and also off-the-shelf binaries, and achieve good, compatibility and performance. And that's what I was talking about earlier in terms of building up the right teams and the right tests and the right tools. And then once they're able to do that, they're not breaking their workflows from on-premises. That then opens the door for them to explore things like re-architecting maybe a subset of their workflow to take advantage of some of Google's advantages. So a lot of the work here really was around just meeting customers where they are versus saying, hey, come do it the Google way or come do it the cloud way.
Yeah. Now, one of the things that I wanted to talk to you about in particular, because you've been in HPC for a really long time. And I was at supercomputing last year and noticed that the entire energy of the conference shifted. HPC seems really hot right now in terms of a focus for the industry. What is going on in HPC right now that is driving so much industry attention, and where is it going next?
Well, there's really two parts to it, and it's also two letters. It's AI, right?
Okay.
So the first thing is these large language models. There's been a lot of innovation over the last decade now. It's amazing that it's been a decade almost since some of the seminal papers came out around transformer and attention architectures coming out of Google's DeepMind and other researchers around the world. It's just been an explosion in AI research. But fundamentally, artificial intelligence training of these large models is an HPC workload, meaning they require supercomputers. And that's why we've seen this explosion in the industry of demand for accelerated systems that are able to run these models. So we see it, I'd say, most prominently with things like GPUs coming from NVIDIA and AMD. We also see specialized processors that have been purpose-built for AI, such as Google's own tensor processing units, TPU. We're on, I think, we just announced our 8th generation, right? The other thing, though, that's really happening in the high-performance computing community, and when I say HPC community, I really mean scientific and technical computing community, people who are solving problems that are grounded in math, right? And the laws of physics, the laws of chemistry, all the way up the stack to biology, the hard sciences, or other technical computing areas like rendering special effects in films, or program trading in financial markets, weather prediction, climate modeling, the application, drug discovery. The applications are endless. And what's happening is people are looking at AI as a tool to accelerate their discovery. So that's coming in. Folks initially thought of it as artificial intelligence was going to be kind of an assistant. It would help you dig through papers faster. It would help you analyze results more quickly. It would help you prepare inputs to your applications more quickly. But what's really been exciting over the last about year or so is the development of agentic systems and multi-agentic systems, where we can do hypothesis generation. We can take ideas that are grounded in a researcher's own field, and she may have graduate students who need a novel idea, being able to take an existing idea and vet it, or take an area and say, what are some new things I could explore that are consistent with my group's capabilities in research? So that's really been where the conversation has been lately, is around these multi-agentic systems. And then finally, just as large language models have become incredibly powerful by training on massive data sets of text or images, what is the analog of that in science? Can you train a model on the body of scientific literature, experiments, experimental data, simulation data, and now get predictive capabilities? So that's another huge focus in the industry right now, and it's causing seismic shifts in the way people are thinking about how they do science.
Now, you talked about in AI integration in math. Can you just take one step back and say, you mentioned Google DeepMind, and obviously very famous efforts from Google DeepMind in this arena, including, winning a Nobel Prize for some of the advancements that they've driven into the scientific community. Can you talk a little bit about the difference in math and AI and traditional HPC, and why this is such a attractive combination? And then also, from an agentic standpoint, when we're thinking about training hypotheses, how does that implement in terms of how you deliver the services that you're delivering in Google Cloud?
Okay. I think the main difference is, and again, I think of it all as high performance computing. In the early days, scientists were doing things on pencil and paper, right?
Hmm.
Or programming single machines to do the math. And at some point, I think most people know that Fortran stands for formula translator, right? It was a language that was built to help scientists put their math formulas into computers in the 1950s. And obviously, the field of computational science has developed and really got sophisticated with solvers for finite element analysis and many different methods to solve partial differential equations, working directly with the laws of physics or phenomenological data and methods that have developed. So I would say the workhorse of HPC for the last decades really has been modeling and simulation, right? Direct numerical simulation. It's been augmented, though, by other things such as visualization, analytics, right? And so I think of high performance computing as a practice. It's an activity that someone is doing to try and gain insight where very powerful computers are involved. So AI is really just a new tool on that landscape. It hasn't really changed the types of problems that people are solving or their desire to solve them. It's offering an ability to become more productive. And one of the key ways is through its predictive power. So I think a good example would be some of the research that came out of Google DeepMind recently. And when I say recent, I mean the last couple of years, around weather forecasting, right? This is another place where we have a vast store of historical data, right? We have both the observational data, and then we also have the predictions. So being able to provide something like that, those data sets that come from organizations like the National Weather Service in the US and ECMWF in Europe, and train AI models on them so that they can actually do multi-day forecasts has been very, very successful. But the thing that makes it most exciting is that a traditional numerical weather simulation might take hours on hundreds of processors to generate, say, a 7-day forecast, and they need to do this every 4 hours or so. These AI models that have been trained, you can make those predictions in a matter of minutes with much, much smaller amount of compute resources. So AI holds the promise to accelerate the exploration of, say, the design space for automobiles, aerodynamics, or quickly give you an estimate of the weather. Ultimately, if you're doing something where safety is involved, or you're going to build a product where you're going to stamp out thousands and thousands of these, you still want to go back to get as close to the ground truth as possible by running numerical simulations for validation.
Uh-huh.
But AI can play a role that helps you really winnow down the space to the most promising candidates in designs very quickly, or get a quick look at what the weather forecast is going to be.
Now, I know that Google got into cloud computing relatively late compared to the other hyperscalers, but you've really grown from really had a meteoric rise in terms of your capabilities for HPC. You've really stood out in the marketplace. How have you done that in terms of what your key moves were in terms of establishing and growing services, or any particular inflection points that allowed you to engage the HPC community in unique ways?
Well, the approach that we took, and this was my focus when I arrived, was recognizing that HPC users are not single application users. Right?
Mm-hmm.
Most HPC centers are shared resources, unlike IT, where maybe you have a collection of servers, and it could be a small number, a very large number, that tend to be devoted to individual applications or individual services, tend to run at relatively low utilization on average in order to absorb the spikes that happen from time to time. Cloud was really built around that notion of how do we consolidate those workloads onto fewer servers, taking advantage of techniques like virtualization. And that's kind of like the opposite of what high performance computing is, right? High performance computing is about aggregating resources to solve a single problem more quickly. But because they're such expensive and capable resources, they have to be time shared. They have to be space shared, right? So anyone familiar with HPC will know that you go to a computing center and you wait your turn in the queue, right? So that you can get access to a slice of the machine for a certain amount of time. So those machines have to be typically more heterogeneous in terms of their design. They have to be very general purpose. They can serve many applications. So a lot of making cloud ready for HPC really came down to to ensuring that we were building compatible systems and doing it in an automated way so that people could bring their workloads and not have to become cloud experts. And so that's where a lot of the focus was. In order to do that, we had to build benchmarking teams. We had to establish the right relationships with the software vendors in the industry. We had to go look at the difference between object storage and traditional parallel file systems, bring in high performance networking in a way that's compatible with cloud security, building MPI that is fast and runs RDMA, but doesn't necessarily mean overhauling Google's network with an InfiniBand card, instead adopting the principles of InfiniBand, making them compatible with our network. And then finally, I think one of the biggest open challenges is still storage. But generally, just looking at the way people solve the problems in HPC, high utilization, getting the economics right is really, really important. HPC users have very different expectations about what compute and high-performance computing should cost than, say, a traditional IT shop. And it comes down to those utilization rates I was talking about earlier. One thing that we do differently is we really approach our customers acknowledging the value of their on-prem systems, acknowledging the pride that they have in systems they built, and then come in with the question of how can cloud help, as opposed to necessarily replace those systems. And that different approach has also been a great way to engage our customers a little bit differently than some of the others in the market.
No, that's an awesome explanation. And one of the things that I think it'll bring it to life is if you're working with a large supercomputing center that's looking at using your services for their workloads, how do you partner with them to get this actually stood up and on real-time work?
Well, we approach this with multiple phases. There's, the introduction, and I think the most important thing there is ensuring you show up with people who have experience in high-performance computing and can speak the language. So the language of high-performance computing, just the vocabulary, that's used, the way we talk about it is very different than the world of IT. And so building credibility by coming in and talking to customers and having them very quickly understand that this is the first time we've seen their type of environment, their type of problem. That's the first thing that really needs to be put in place, and making sure that we have that conversation where we acknowledge the value and of what they've done and their role in doing that. We're not here to replace you or threaten your job. We're here to actually make you more capable of getting you a richer set of tools to offer your users. That's really important. So after establishing that credibility, then we really need to bridge the gap between their deep understanding of their domain, high-performance computing, our understanding of high-performance computing, and then specialists that we have a deep understanding of cloud computing, right, and then bridge that. So a lot of times it will involve doing the very early things, what we call establishing a foundation, or sometimes a landing zone. And once that's in place, we've built tools that allow customers to express their high-performance computing environments in very familiar terms, and do it in a very modular way. And this is another thing that we've done a little bit differently than others in the market, simply because we came along later and we're able to look at what customers were liking and not liking. So we have a product called a cluster toolkit, Google Cloud Cluster Toolkit. And this actually allows you in very natural language, what's known as a YAML file, with many, many different examples, to just very modularly put together systems that you understand. So you can say, this is my NetApp, or this is my home directory with NFS, this is my network, and build that virtual data center. And then the automation of the tools goes and writes all the low-level code to interface to the cloud APIs. So as a result, many of our customers never write a single line of cloud code or make a single cloud call. They instead use these tools to create the environments, including the schedulers. And then finally, the way the cloud business works is that, we realize revenue when customers use our services. It's not like a traditional supercomputing purchase where you deliver, accept, and get the revenue. And so post agreement, I would call it, we have teams that are dedicated to our customer success and will help them unblock, whether it's a technical issue or guiding them to the right regions to achieve the right performance, cost, availability of resources. So it's a full life cycle engagement with the customer.
Bill, it's been great to talk to you. I think I've got one more question for you. And it's interesting to listen to you because I know you've worked in so many aspects in high performance computing, from developing the foundational compute for high performance computing, now delivering cloud services that are uniquely designed for high performance computing. We're heading into ISC. and obviously a key moment for the high performance computing industry. Can you just give us a preview of, what comes next? We talked about AI, agentic. What are you looking forward to from hearing from the community, and how will that inform what you do next with your team at Google Cloud?
Well, we really tend at these trade shows like ISC and supercomputing. They're academic conferences and they're also trade shows. We do a mix of activities. We engage with our customers, oftentimes directly at our offices. So this year we'll be hosting a Google Cloud Advanced Computing Day with hands-on training and educational materials at the Google office. If anyone's interested in that, I think there's still room maybe for a few more registrants. We do it through our receptions where we engage directly with the community, meeting leaders and bringing them up to date. A lot of times the most prominent leaders are also the ones who are busiest themselves in getting briefings. And then, of course, we have our briefing rooms where we meet with customers and share information that's maybe more sensitive that we're not ready to discuss publicly, but we can tell them is coming. I think some of the most exciting work that we're doing right now is working towards making productization of Google DeepMind's co-scientist under the Google Cloud product umbrella, and also Alpha Evolve, which is a technique to take the existing solutions to problems and use AI-driven evolutionary algorithms to optimize. And we've got some really exciting case studies in that front. So I think what we're going to be looking at is a couple things. One is really hearing to what extent people are adopting these things and having success. What are their outstanding needs? The AI revolution has caused us to really do some innovative things, for example, in file systems where we can have block storage that thousands of clients can attach to and read the same software library or data set. Very important for machine learning. What are the applications of that in areas such as drug design, electronic design, automation, anything where you have large shared libraries and large shared data sets. The other thing I think that's really going to be a big part of the conversation is AI is now driving the hardware roadmap, and we have a panel that we'll be leading. And the question is, how do scientists survive in a world where the machines are getting faster, but they're getting faster on low precision math? But in order to really get the right answers in scientific computing, we need high precision math. So how is the application and library and methods landscape changing? And does the scientific community have a handle on that? Or do we need to be changing our trajectory as an industry to ensure that they have access to the high precision compute that they've had in the past?
That's amazing. I can't wait to learn more about what you're doing at ISC and what you're doing in terms of delivering value to your customers. And I'm sure that the folks who are following online want to engage with your team. Where can listeners go to learn more about Google Cloud, the services you're offering for HPC, and engage in conversations about adopting your services?
Well, I think that one of the things that folks will find most interesting is, I've just touched on a handful of these topics in the last 20 minutes with you, but we have weekly meetings of what we call the Google Cloud Advanced Computing Community, and those are hosted by Jay Boisseau, who's a prominent member of the HPC community as well. It's in our team. And every single session involves either leaders from Google, leaders from the community, or some of our own customers sharing their stories. And every episode is recorded and posted to YouTube. So not only can you sign up for the community and start to hear more in depth about the topics I've been talking about and what's happening, what's coming, but you can also go to the library historically. And the other opportunity that I mentioned was if you sign up for the Google Cloud Advanced Computing Community, you will also have the opportunity to come attend our briefings and our receptions at ISC this year. That'll be a great place to get engaged and learn more.
Awesome. Well, Bill, it's always a pleasure to talk to you. And today was no different. I learned a lot. So excited to see what you're doing at Google. Keep up the fantastic work. And thank you so much for your time.
Well, thank you for the opportunity, Alice. It's great to see you again.